Good morning, ladies and gentlemen. Once again, we are resuming this session now. So without much delay, we are moving to our fireside chat. This fireside chat session will be going to discuss briefly on accelerating innovation in sustainable aircraft design. Let me introduce our moderator of this session, Mr. Amit Agarwal, Director Technical ANSYS and Asia ANSYS India and Asia Pacific. Mr. Amit Agarwal leads the technical team of ANSYS India, serving customers across India and Asia Pacific. He works closely with strategic customers across industries and has led many crucial campaigns for ANSYS India, including one of the customer retention, new and emerging products, and the global campaigns on customer success stories and industry's best practices. He has also initiated successful campaign on academic relationship and key account development. In his earlier role, Amit was instrumental in developing an industry-focused sales and technical team at Fluent India, serving India and Southeast Asia. He has worked closely with key academia, private and government organization, and multinational design center across industries in India. With BTech Aerospace Engineer from IIT Bombay, Amit has been with ANSYS for 25 years, having started his career with a former Fluent organization. Now I request Mr. Amit Agarwal to take over the panel and moderate the session. Over to you, sir.
Thank you, Hassan, for a very nice introduction and good afternoon, everyone. So we had a very nice panel discussion before this and a lot of elements were added by the earlier panel. So before I get into the fireside chat, I would like to introduce my fellow members in this fireside chat, starting with Mr. Gupta Kancham. Mr. Gupta is based in India. He's joining UK through his business travel. So thank you, Gupta, for joining at a very early morning from UK. So Mr. Gupta Kancham, he's Associate Vice President at SAEIND. He's the delivery head for the Aero Engines practice at SAEIND and has been working in Aero Engines domain for last 20 years, actively sourcing partners in gas turbine engine development. He had a couple of publications in the area of simulation. He's been an early adopter of RPA in engineering simulation and has been driving digital transformation in the area of MPD, digital thread, industry 4.0, platform-based AI/ML solutions for aftermarket area. In his earlier career, he worked as scientist at the Department of Atomic Energy, instrumental in deploying high-speed rotors for strategic application, turbomachinery applications for cryogenic engines. Welcome, Mr. Gupta.
Thank you. Thanks, Amit.
And let me move to my next fellow colleague, Mr. Guram Venkateshwar Rao. So Mr. Guram Venkateshwar Rao is Senior Engineering Section Manager, leading Advanced Design Tools team at GE Aviation. His team develops very complex physics-based engineering design, modeling, simulation software tools and methods for GE Aviation and GE Power business, and has over 21 years of experience in engineering design, technology development, and leading teams in engineering. Mr. Guram joined GE Aviation in the year 2000 and spent first 15 years in the area of heat transfer, secondary fluid system design, and developed significant role in advancing the thermal systems design and technology. After spending 15 years in heat transfer area, he moved to services engineering and played a significant role in building fleet engineering teams and led the engineering support to maintenance, repairs, overhaul, shops, and the airline customers. Currently, he leads the advanced design tools team at GE Aviation. So welcome, Gaurav.
Thank you, Amit.
Yes. So before we take a dive into the fireside chat, I just want to take a few minutes to recap what we all heard from the earlier panel. And we had panel members from same industry, and we will pick on the thread which they laid out. So it started by talking about no matter how efficient planes, engines we make, the demand on aviation is growing. We heard about doubling of airplanes in a very short duration. We also heard about a common footprint coming from design manufacturing on one hand and the operations and disposal on the other hand. We heard about multiple technologies, including the conventional ones, for example, lightweighting, composites, drag reduction, efficiency improvement. We heard about blended wing aircrafts. We also heard about new investment in the area of high bypass ratio engines, sustainable aviation fuel. We spend a lot of time, hybrid electric propulsion, hydrogen-based propulsion, and even advancing the gas turbine cycle, the Brighton cycle. So the earlier panel also emphasized not just design development, but also need to look at certification, cost, and reliability. And it raised questions with respect to how to use engine power into the system and to explore alternate power source. Then it spoke about data and technology for better routing, where we can also put it to use for better sustainability. The last two things which I want to emphasize came from an ecosystem point of view. You need to work with startups on innovation front and developing the right talent and expertise. So very relevant points raised in the earlier panel. With that, let me start with Guram. Guram, GE has been at the forefront of improved engine design, and we heard this from Uma a few minutes back. Can you just pick on that thread and elaborate GE's experience on past decades, and what are the new frontiers you guys plan to get in? Just building up on where Uma left.
Yeah, thanks, Amit. First of all, I'm really privileged to be part of this panel and would like to thank SAI team for inviting me here. So coming to your question, Amit, and I will divide this question into two parts. One is GE's experience of building efficient engines, and then the second part of the question is on what are the new frontiers GE's plan to achieve, right? So I'll start with my first part of the question. I mean, GE has been always focusing on developing and maturing breakthrough technologies, and which are basically leading to improving the fuel efficiency and thereby reducing the carbon emissions. If I start with some statistics, LEAP engine, which is coming from CFM, which is GE Safran joint venture, which is basically powering Boeing 737 Max and then Airbus A320neo, has 15% lower fuel consumption and then 15% reduction in the CO2 emissions compared to its predecessor engine, which is CFM 56. And if I pick another example, GNX, which is powering Boeing again 787 Dreamliner and Boeing 747-8, which is also having 15% the fuel efficient compared to the previous GE CF6 engine. And 9X, which is going to power Boeing 777X. Okay, so this is also will have 10 plus percentage of fuel efficiency improvements compared to the GE90, which is powering today Boeing 777s. Now the question is, how are we making these improvements, right? So we have used focus on in advancing the propulsive efficiency, then the thermal efficiency, and the technologies needed to increase or improve these efficiencies, right, in the areas of engine architectures, aerodynamics, materials, right? On the engine, if I talk about briefly about engine architectures, I think Uma spoke a little bit about high bypass engines. So basically, you get more flow, more thrust, and then resulting the higher propulsive efficiency. So that's kind of a focus on the architectures. And of course, with all the advancements in aerodynamics, right, I mean, we are able to come up with designs with very high pressure ratios, which is basically resulting higher thermal efficiency, right? And the third aspect is on the materials and the manufacturing, right? With the invention of the composites on the fan blade side and ceramic metric composites, CMCs, and of course with additive manufacturing, right? I mean, these are all things helping us to improve the fuel efficiency and reduce the emissions. And now, if I coming to the second part of the question, what are the new frontiers GE plans to achieve or is working on? I know Uma actually spoke in the previous panel very nicely about the 5 areas. Maybe I'll just quickly touch upon them. And you all would have seen last year, mid of the last year, GE Safran together launched a CFM RISE program. Basically, RISE stands for Revolutionary Innovation for Sustainable Engines. So the objective of this program is it's a basically technology development program, focusing on developing the next gen breakthrough technologies, aiming to reduce more than 20% fuel consumption and CO2 emissions compared to today's efficient engines, and at the same time make sure these engines are compatible with alternate energy sources like SAF. A lot of good talk on the SAF, sustainable aviation fuels, and then the hydrogen, right? Um, if I little bit elaborate on RISE program, what are the areas this program is focused? One of the area is on the architectures. So we're talking about the open fan architecture, pretty lengthy open fan blades. We believe this is going to be a big step change in the propulsive efficiency, right? And the second area is on the thermal efficiency side, advanced metal alloys, CMCs, right? And the third area Uma spoke about also the hybrid electric development, of course, to further our engine efficiency and to create opportunities to fully electric aircraft. The fourth area is hydrogen combustion. Again, Uma mentioned about the collaboration with Airbus on hydrogen demonstrator. Right, so these are all areas we're working towards making the sustainable aviation. So back to you, Amit.
Thank you, Guram. Thanks for those interesting inputs. Can you just briefly, continuing that thread, comment on role of engineering simulation in this journey?
Yeah, no, the simulation is actually played a huge role in developing these next gen engines. I mean, we can't do testing for each and every concept, right? I mean, the testing is pretty expensive. Yeah, so simulations with coupled with advanced, I'll say the computational capabilities are really helping us to capture the complex physics and also perform. The previous speaker spoke about the multidisciplinary optimization, right, which is a very important aspect in terms of coming out with optimized designs. So I'll probably pick an example, how the simulations really help to advance the designs. So the example I'm picking is the composite fan blade. So we introduced composite fan blade in the G90 program. That's sometime in 1995. So we had 22 fan blades when we introduced. And if we come forward in the GNX engine, which was developed after G90, so we have reduced the fan blade count from 22 to 18. And the 9X engine, which is going to power Boeing 777X, so we have now 16 fan blades. I mean, how is it possible to reduce this blade count? Right? I mean, the simulation, has really helped us to understand again this complex physics better, and also to come up with the best 3D aero advanced designs. Thereby, you're able to reduce number of blades, and that means reduced weight and resulting higher fuel efficiency, right? So simulations, in my view, is really playing a very important role in terms of advancing the designs.
Thanks a lot for
Thanks, Amit.
sharing a very real life scenario for the benefit of audience. So with this, let me move to Gupta. Gupta, can you comment on your experience working with global companies in sustainable design? And what are the new frontiers you see in sustainable aviation, especially the propulsion part?
Thanks, Amit and SA for giving the opportunity. Let us say sustainable. Okay. So now the design philosophy, really what we have that need to be kind of a changing to design for circularity. So where, we need to really, the focus is on how really we can repair, refurbish, remanufacture. So that's the one kind of a thing where complete design cycle where we need to change. Okay. That's the kind of a, the basically design for circularity is very important. And the other role is, the repurpose. Earlier, it was kind of a one component for the one purpose. In the design for circularity, again, we'll see for that how really we can repurpose the some of the components. And the last resort is a recycling. So basically, it works on the 10R principles. Okay, reduce, refuse, resell, repair, refurbish, remanufacture, repurpose, recycle, recover, remind, and refuse. So there is a total 10 R's of where, under design cycle we need to really kind of a couple. Okay, but the what really important here is a very traceability. Okay, the traceability and the digital connection where a lot of simulation really kind of a also the play a role. How really digitally all these things be connected so that the traceability is very important. Okay, and the energy consumption optimization is really also important. So they more and more, definitely we need to different scenario, we need to really kind of simulate and ensure that we really take the kind of a complete full life. It's a life extension. Like I say, for aircraft engines, one of the part is a life extension. That's a very exclusive simulation activity, because while we design the kind of aircraft engine parts where I majorly involved, we really kind of do for the limit cycles, right? Then in the practical condition, it will be little different. Now you take the data from the field and simulate and estimate the life, so they can really kind of extend. That's one method. There are several methods. Just I'm taking and the absolute management and the reliability, repeatability. So all these, all the simulation intense activities. So how really we can do it? Okay, that's the first part of the question. The second part of the question is on the new frontiers. So the basically, if you see that, while there is a improvement of the all the OEMs working, all three OEMs are working, the the opportunity is a very limited for the conventional gas turbine. Okay, and it requires to push a lot of the limits. If you want to really kind of push the pressure, definitely a lot of manufacturing cost and the materials, all the new materials and the temperatures and the high pressure base ratios. So while these are the three levers available, but with kind of a very limited opportunity, the way we see. Okay, and the other one is also that's the one aspect. The other aspect is the right now entire aviation industry contributing at 2% of the carbon. Okay, for the global. Okay, and this is anticipated to grow around 5% of the growth for the next few years, at least next 10-15 years. And as an industry, I think they committed to reduce the 50% of the reduction. Okay, so all these really kind of calls for there will be an alternative the to the fossil fuel. It could be biofuel or the hybrid electric, where electric the systems take a little longer time. I think the earlier discussion we spoke, but whereas the hybrid electric is very kind of a very near future, it's possible. And this also helps to reduce the noise reduction and low maintenance. But of course, so that need to be kind of then we can really see that how really kind of the simulation helps here, right? So one part, if you see that, the power distribution, thermal management, and the coupling of the electric motor along with the GT engines, okay, and also right from the packaging and poor electronics, and how really I can pull the power distribution. So if you see that almost kind of a 7-8 kind of a subsystems really need to mature and manage, and everything is not possible in a conventional way of try something, design something, manufacture and testing. I think a lot of optimization has to happen through the simulation. Either it could be thermal management to the power electronics or soft motor coupling. All these, they are the new things really we need to really establish the technologies. They are very advanced, but still it's a kind of in the development stage. I can say any level between the tier level 1 to the level 4 stage, and the especially from the 4 to 6 also really we need to use lot of a simulation now. That really helps, because that reduces the cycle time and overall investment, because everything you need not to test and manufacture.
No, this is very nice. And if I can request Guram to take just a minute or two to deep dive into the hydrogen part of it. So we heard a lot about hydrogen propulsion. We also heard about fuel cell, but your view on hydrogen propulsion.
Okay, so very brief on the hydrogen. I know the previous panel speaker spoke about some of the challenges hydrogen is going to bring. We all know hydrogen is carbon-free fuel, so that's where we can use hydrogen in our conventional engines replacing jet fuel. But now coming to its characteristics, right? The previous speakers also alluded, when hydrogen occupies 4 times more volume compared to the jet fuel for the same energy content. What it means is because we need a larger I'll say the cryogenic fuel tanks for carrying this liquid hydrogen. So that's going to be a big challenge there. And then, the challenges with respect to infrastructure, supply chain, and even the producing at that scale, right? I mean, if you want to convert hydrogen, let's say from gas to liquid, it's a pretty complex and I will say the energy intensive process. And creating that level and then having the distribution supply was going to be another big challenge. But that's on the high level infrastructure and supply chain. But if I talk about hydrogen as a combustion fuel, right? I mean, we know hydrogen is very reactive in nature, right? And this hydrogen combustion has its own challenges with respect to the combustion characteristics. You talk about auto ignition, flame speed, or flashback. The engine combustion dynamics is going to be another big challenge, and of course, the controlling the knocks coming out of it, right? I mean, all these challenges has to be worked upon, right? Um, I think, yeah, at high level, those are the challenges which brings for the combustion side. Um, yeah, well, back to Amit.
Yeah, thanks. And Gupta, if you can pick the thread on the hybrid propulsion side, what is your view?
See, the while everybody wants the complete electric, the reason is the first as a step is the hybrid, because if you see that for the any kind of a general passenger like Indigo or something, we read the energy density of 1800 watts per kilo, right? So right now the our current battery capacity is around 200 kg per 200 watts per kg. So there is a lot of development need to be done. But however, see, in meanwhile, the way it is going to take is the what is the peak power? Like if you see that there is a huge difference between the GT engine design for the takeoff to the cruise. Okay, now a lot of gain you can get it if really somehow supplement this the additional the power requirement during the takeoff phase. I think that's where really kind of a lot of concentration now, how really we can go for the hybrid so that we can maximize the efficiency with the minimum, even the limited possibility, because that's what the kind of it become a light design of the general GT engine. And so that saves a kind of a lot for the fuel efficiency as well as the overall the energy efficiency we can get it. Okay, so I think the way I see is, so in the next 7 to 8 years, hybrid could be kind of a reality, and kind of a 2020 late 20s or 30 early 30s, and eventually it will go to the kind of a full-fledged this one.
Wonderful. And just continuing that thread, as you very well know, digital transformation has been playing a key role. Can you comment on science experience with digital transformation, where you've been applying it and the role simulation has been making?
Yeah, okay. If you see that, welcome to the digital, this one sustainable, right? There's a topic, right? From there, the traceability is very important. Okay. Then the overall, the way it need to be really kind of a connected is kind of model based engineer enterprise. Okay. In order to really kind of you need to really maximize, okay, either in the during the design phase to reduce the efforts, or the manufacturing stage, or the operation stage. All three stages typically entire OEMs operating in the three different buckets. Okay, there is just some kind of a connection is required. So then the model based enterprises really kind of gives the platform or first step in a say to enable the digital thread. So entire modeling has to be done, and the right from the CAD to the CAE to the and pass on to the manufacturing and the inspection, then it can go to the operations and go on. Okay, so I think the basically right now the way I see is from the conventional the earlier CAD, CAE, and the manufacturing, three different worlds. Okay, that need to be really kind of a connected. Okay, so the simulation connection is very important in that aspect. So the conventional 2D drawings to the kind of a how really kind of you go for the 3D the models for the manufacturing, and also two independent models for the not the quite different, from the CAD model to CAE model. But I think the now the CAD CAE tight integration is also a very important aspect where a lot of advancement been done. And also, if you see that within the simulation, all of us know that we're living in this world. My model for the aerodynamics is different from my thermal simulation, different for the lifing, right? So these are the three independent, typically, or for whatever reason, to optimize their simulation time and get the best results. So we do have adapted three different models. I think with the latest competition available, lot of thanks to the and since other people, lot of advancement been done. Okay, now it will become a over the time, next few years, it will be reality. We will have a unified model for the both for the CFT thermal and the typical stress analysis. Okay, if we are not there, but we are towards the direction to make the have a single unified model, like a single data, right? Yeah.
Thanks. I think you touched on a lot of useful points, essentially covering the design very quickly about the other elements, manufacturing and operations. So let me turn to Guram. Guram, can you elaborate a little bit on the operations aspect? What I mean is maintaining an operating engines in a sustainable manner is very critical. And what is that G is doing in this area under the purview of MROs or engine utilization?
Yeah, so I'll briefly touch upon few things here. So we work very closely with airlines, basically in providing solutions that help them to reduce the fuel consumption and improve the flight path navigation. Reduce the time between the destinations, and of course avoid maintenance disruptions and keep the fleets running efficiently. Right. I mean, if I pick the maintenance insights, right, because these maintenance insights provides basically the airlines help them to understand and monitor the component health to optimize the performance and to decrease inefficiencies. Of course, that inefficiencies lead to the excess fuel burn and then carbon emissions, right? So other aspect of maintenance insights also helps the operators to avoid this maintenance disruptions, so that we can actually keep their flight, existing fleet running efficiently and reduce the carbon footprint. There's a high level, few aspects we do in terms of operating the engines in a sustainable manner.
Good. Thanks, Guram, for sharing that aspect. And Gupta, if you could complement from manufacturing and also your views from a operations point of view very quickly.
Okay, let me answer second question first on the operations. Okay, let us see if all these engines, okay, operate, right? There are three kind of a different data sources, right? One is the how this is being kind of a manufactured. That's the one kind of a data. Then how this been operated, right? Any kind of a events, any kind of a aberrations, or any kind of a these things been done in the field that we need to really kind of a capture. Okay, then the how the on the daily and the everyday operations, every cycle operations, we see kind of a there is a lot of data being generated. How they kind of a the T3s, T1s, P3s, all how this overall performance been there, fuel efficiency. Okay, right now we are working our OEMs. How really kind of a we can integrate all these three things to really kind of a give insights. If there is some kind of a the from the with all this data collecting and on the putting under the a platform for the leveraging the A and ML, really you can get the insights. The how really kind of a one engine need to have a shop visit, or in that particular engine, even to the level where we could go is particular component you need to replace by the X cycles, so that a lot of planning can be done, because these are the kind of a very high of the value and a limited lost long lead of the components. Let us say somebody has to replace the HPT router. Okay, it is not easy. The lead time is a 6 months, or something need to be repaired. The right from the MRO shop to the repair shop, capacity planning and getting the slot and getting and all is also very kind of a the asset incentive right, is a very high cost. Their utilization is very important. So one is how really we are integrating, we are collecting, colliding the data in single database and having the ALML platforms to get the insights. That's the way really on the wing, the time has been extended. That's the one kind of a solution where really kind of a we are working with our OEMs. Okay. The second thing is, as you know, that all these are the very kind of a highest certs, how really entire asset optimization. Okay. Within the MRO, how really the kind of entire assets can be optimized, and over the kind of a the for the leasers or the OEMs, how really their entire asset being kind of utilized. So the other aspect of the solution we are working on the how really we can optimize the SAT. The same philosophy. You need to sensorize through the IoT and get the data and get the insights, and so that really kind of entire optimization can be done. Okay, so these are the two major things. So right now we are working.
Thank you. This is very helpful. Now we are coming gradually towards the closing. Question is to you, Guram. For the audience who's attending, what would be your final comments on the key thrust areas, maybe top 2, 3, which are making a big difference under sustainable aircraft design?
Yeah, I will say, we have a noble cause in front of us to create this sustainable aviation. So in my view, the next 2 decades, aviation industry will really go through the radical technology changes, right? We spoke about advanced architectures, hybrid electric, SAF, hydrogen, and then, the fully electric. So I'll say it's a very exciting time to be part of the aviation.
Thank you. And moving to Gupta, you have covered a lot on operations, manufacturing. What would be the top 2, 3 areas under the purview of operations, manufacturing, which will be critical for sustainable aircraft design, development, manufacturing, and operations? If you could cover that.
Yeah, see that, the one is on the complete again sustainable coming on the refurbished use. So conventionally, additive is developing, right? How really we can leverage additive to kind of a repair. So that's one point where the kind of the coming to the sustainable, right? So there's a lot of similar, because historically we have been kind of a wide to design for the conventional manufacturing. That again the simulation really helps with a new kind of a the design techniques, how really kind of a the we can really kind of a design using additive. That's one part. And on top of that, right now, the early research we are also working with our OEMs is how really can leverage the additive for the repair. Like either could be a compressor IBR or the turbine. These are the very expensive parts. All of us know how really we can leverage. That's one part where it allow according with the simulation, digital advanced technology, how really can take it. That's coming to the manufacturing. Of course, so but the putting all the sensors for the greenfield engines, having it ready for the industry 4.0. So because on the overall digital thread, in order to kind of a traceability, all this is important. There's the connection, right? That's very important. The way I see is the future, in immediate future, improve the traceability. There is a digital thread need to happen, and everybody is working. We are on the path. Okay, then the MBE is really kind of really going to enable a digital thread in the aerospace industry. That's the one takeaway immediately, either for the design to the manufacturer to the operations, we need to really adapt that. That's the near term. That's one thing. On the if you see that little longer time, definitely the air taxis or the hybrid or the hydrogen in the next 7 to 10 years will become a reality. Okay, I think just the way I see is that we are a little behind the car auto industry. Oh, of course, the scale is much more. It will take a time, but still we also will be in that particular transformation, complete how the propulsion can be kind of redesigned.
Thank you. Wonderful. So you both have touched on all aspects, starting from design, development, manufacturing, and operations. And the opportunity is immense with the demand for aviation sort of soaring through the roof. I think that kind of brings us to the end of this discussion. But Before we wrap up, if there are any questions, Hassan, can you read up? I'm not able to see the questions here.
Yes, sir. There is a one question from Arun. Uh, if any of you are looking solution in harsh environment in such very high temperature or severe mechanical, oh sorry, that was a promotional mailer. Ilungo sir, can you scroll up? There was another question from Mohan Kalepa. Yes, sir. There is a question from Mohan Kalepa. In your experience, what is the correlation or confidence level between simulation and real world tests? That was the question.
So that's an ideal question for Guram. Can I request Guram to comment? He actually, that's his daily life. And then Gupta, you can add your comment.
Sure, no,
Yeah, yeah. I mean, I think start of this conference, right? Dr. Balbharadwaj spoke about simulations and then the people aspect it, right? And it's both are very important. It's tied together. And in many areas, we actually reached a stage we're able to predict very close to the actual scenarios. And there are of course some areas where we're still understanding. I mean, if I pick about hydrogen, which I spoke, a lot more things to understand, right? And that's where of course we're working with partnership with others to understand the physics, what's happening in the domain for the simulation aspect, right? So but I mean, if I say in some areas we are very close, some areas probably there's a lot more things to understand and capture that physics part of the simulations.
Thank you. Gupta, your inputs, please.
Okay, if you see that simulation, when we started, maybe I started around 20 years, right? Number of tests required for the blade outs or the lifing or the endurance quite intense. So it's been a lot of reduced. Okay, that's because what are the advancement we do in the simulation? If you see that, the current state, the kind of there are few parameters like a strength, lifing, pretty much we're very close. Okay. Whereas on the thermal, still it's kind of a 50 to 100 degree variation. Okay. Well, CFD being kind of a replaced with our kind of a conventional estimations of the heat transfer coefficient, it's been reduced, but still there is an opportunity. Okay, right? So, but still I need to have a multiple tests right now. Okay, as we speak, right now we are working with our OEMs, really, how really the new concept what we are working is the model-based testing. So what really it essentially do is, okay, leverage the data analytics and our the multidisciplinary optimization and the number of sensors. Okay, there are two dimensions this one. Okay, we do have, if you see that all the OEMs have a last 50 years data, 70 years data. Okay. The entire project talks about, the simulate, okay, and see and correlate with the what is the existing data, then really see that, how really I can do the optimized number of sensors and also the number of tests. Okay. I think to answer your someone's question, okay, in certain aspects, definitely simulation is reached a very good state. Even on the blade outs, earlier we used to tell 10, 15, now it comes to 2, 3 based on the kind of a what kind of a the redesign or design is going to vary, but quite a few reduced. Okay, and still there is an opportunity to reduce
Yeah.
further if really kind of we can the estimate correctly on the thermal and CFD with a lot of computational technology available. Now, but there is a feasibility. I think the right now, the I think the our aim is next 5 years, can we reduce the 50% of the testing? So I think that is the project where we are working on the model-based testing. So basically, marrying data analytics along with the MBD of model-based simulation and correlate the design optimization and correlate get insights so that new planning can be done.
Thank you. It's been wonderful. So in the interest of time, we will wrap up here. Thanks a lot again, Guram and Gupta, for joining for this session, taking the time out and sharing your learnings from field. So with that, I would hand over back to Hassan. Over to you, Hassan.
Thank you all.
Thank you all. Thanks for giving
Thank
the opportunity.
you. Thanks a lot to Mr. Amit Agarwal for the moderating fireside chat and excellent inputs from Mr. Gururam and Dr. Gupta. So before we going for the next keynote address, we will be running a short poll. I request all the participants to participate in the short poll. So, Ilungu sir, can you display the first poll now? Yeah. So the first question we have put it at, does your organization have a roadmap on sustainability? So it'll be having 30 seconds to answer your polls. So can okay, can you display the second question, sir? Okay. So you have put it all questions, sir. So the second question was, going forward, which of the following should be the most important focus for you towards sustainability in commercial aviation? So we have multiple choices of lightweighting, mission engineering, material management, system engineering, and sustainable aviation fuels and alternative propulsion technologies. You can answer your question aptly for that. So, and third question will be, would you like to learn how ANSYS is helping its customer in achieving their sustainability goal, and would you like to be contacted by ANSYS? These are the questions. I request all participants to participate in this poll questions. Lils. Participants requested to participate in the second question on going forward. Which of the following should be the most important focus for you towards sustainable and commercial aviation? Kindly drop your polls there. Half an hour. Thank you for answering the second one, and please answer your third question. Would you like to learn how ANSYS is helping its customers in achieving the sustainability goal, and would you like to be contacted by ANSYS? Please answer your questions there.
Oh. Nana? Chini? Hello? Chini.
Thank you, participants, for your answers. Now we are moving to our next keynote address. So, Mr. Alex Ridgway, Senior Application Engineer, to deliver his keynote technology presentations on maximizing mission performance using digital engineering. Mr. Alex, a senior application engineer, channel partner development manager, and APAC engineer supervisor for AGI and ANSYS company. He supports space agencies, space situational awareness operators, satellite operators, defense and intelligence group in Asia Pacific, Middle East, North Africa, and Europe. Alex has detailed experience working with drones, military aircrafts, communications, electronic warfare, C4ISR, maritime and border surveillance over his 10 years of AGI. With that, I request Mr. Alex to take over the session.
Thank you so much. Can you hear me okay?
Yes, sir. You are loud and clear.
Great. Thank you so much.
Thank you.
Yeah, thank you for inviting me here to discuss about digital mission engineering and about ANSYS itself. I learned a lot today. I'm really happy I joined this group, and it was very informative. And so today I want to talk to you about maximizing mission performance using digital mission engineering. I think the agenda says just digital engineering, but I want to highlight the digital mission engineering, and we'll talk more about that mission later. My name is Alex. I am the International Senior Systems Application Engineer, Development Manager, Supervisor. Generally, I do whatever needs to be done in the international region. I've been working a lot with space situational awareness, space groups, but I've really done a lot with communications, as well as defense and intelligence. A lot of my aviation experience has been in the defense and intelligence realm. So I've done a lot of work with, say, like the Global Hawk UAV system, talked about the F-35 and another Japan's next gen fighters. So I'm kind of pulling into what I know and what I'm bringing in from the defense and as well as multi-domain area and bringing that into aviation. I think that's very important. So a little bit about current legacy processes. And so this is what ANSYS has seen, and this is an ANSYS slide. And what they found is that there is a lot of advanced analytics that are done in a very stovepipe, in a very manual process. Structural analysis is complete, shear strength, and all of those structural components are modeled, analyzed, and then the results are then sent to the aerodynamics group. The aerodynamics group then performs their own analysis and provides that information to thermal. A lot of that, there's dotted lines between those groups because a lot of it is not machine to machine, and it's sending files or recreating something that was done in the other tools. So this process is very repetitive, very manual, and disconnected. And this process works. It has worked for many years in the past, but there's problems with that approach. There's changes. There's speed of life cycles. Things are changing these days that we need to account for and we need to react to. So another part of the actual process is not thinking about design and development individually. Don't think of just your designing group, just your, hey, I'm building one component on top of an aircraft that's doing something. No, you need to think about the full life cycle and the full approach to this project. So right now what we've seen is conceptual development, system requirements and early design. These are all disconnected functions. In the design phase, models, systems, requirements, and physics-based tools are built, designed, developed, and then the system is designed and those tools are then shelved. They're not used again. Then in the testing group has their own tools. Those tools might be an Excel spreadsheet with conditional formatting. That's not really efficient. And it should be utilizing the design tools that were used to actually build the aircraft, build the component. As well as training and operations. Generally, they're forgotten about. We've seen that with some certain disasters recently. I was part of a training and operations group, and I've seen this firsthand where I was not given any materials. I had to build the documents. I was not given many materials. I was given no simulations, no models, no performance characteristics of this satellite that I was going to be delivered. And I had to go back to the early conceptual development phase, early system design phase, and essentially steal the documents from there in order to build my training modules, my training simulations, and my operation simulations. I was never given anything. There was so much time, effort, just too much time lost, so much effort expanded in all of these gaps. And we know that in these gaps, in this process, we don't just go forward in time, we go back and we go from operations to a new concept, from testing back to design. And every time we're redesigning these tools, and it's not efficient. So what we're talking about now is how to improve that efficiency using digital mission engineering. Digital mission engineering is the integration of the mission environment and the operational objectives into the digital thread throughout the entire product lifecycle. This video is showing the whole life cycle of an F-35, an aircraft in theater, in mission, performing. You know, this mission is very defense oriented, and I'm sorry, that's just the content and the materials that I have to explain digital mission engineering. But you know, there are other missions that you can use these tools for, especially cargo missions, passenger missions, UAV missions, urban air mobility missions. All of these missions are essentially similar, and they can all be modeled within our tools. So we take the component simulation, the subsystem simulations, the system simulations, and the system of system simulations, maybe GPS, maybe a communication system on the ground, maybe a radar system at the airport. And we model all of those inside of the mission. It's very, very important. We do all of this so that we can create a digital twin, a digital representation of what's actually happening. So here's that same example from before, the life cycle model, but now the life cycle model is throughout. We don't have the gaps in the design to implementation and the testing to the training. We maintain those models from the early conceptual development phase as we're building those models, building those systems, and we carry them throughout operations and sustainment. The process to, we cannot think of this as a linear approach. It continues to evolve and evolve. And there's also times where these life cycles spin off other life cycles, other development, other design, and we have to consider all of these things. So overall, digital mission engineering requires that you put all of your components, your platforms, your systems of systems, all within a mission, all within a multi-domain physics environment to really improve your overall efficiency, optimize your performance, and just improve safety metrics due to things like traceability. And so now what I'm going to share with you is how to do it. These are kind of big ideas, but what are the direct steps in order for you to actually start the process of digitizing and performing digital mission engineering? Well, the first main step is structural analysis. ANSYS provides tools like mechanical, but there are other structural capabilities and structural analysis tools out there. Those are really important for the stress and strain, and really important for designing and building and testing that system. That also has a very important part of the performance of the vehicle. The shape of the vehicle is directly related to the performance of the vehicle. Are we going to do a lifting body aircraft in the future? How is that going to be developed, designed, and deployed? So mechanical, fluid, they all, the structures and fluids, they all relate to each other, as well as external tools and external payloads like electronics. Those could include radars and transmitters and receivers, very important to understand not just can the vehicle fly, but in what condition. What condition, meaning communication conditions, pilot condition, weather condition, any different condition within the mission. And so what you could do is then take all of these subsystems and some of these subsystems and system models and integrate them together inside of the platform model. Those platform models include, the performance of the vehicle, the fuel usage at different constraints and at different conditions at different altitudes. And it also includes all the payloads, the radar systems, the communication systems, even optical systems. You can include all of them. And then we want to add those to the design reference mission. There's a lot of groups out there that says, oh, my system can operate in a certain, operate like this. They give flat numbers and they say it'll operate here. And then you start asking questions, and they say, well, that's the best it can do. Not it's what it can do, it's the best it can ever do. So by putting it in the design reference mission, can it actually perform as we expect? Can it land in these high altitude runways, low altitude, high winds? There's so many different things, and how can it communicate the entire time? Will the pilot, how will the pilot react if they lose all communication? Those are main considerations. And so now let's start looking at what it looks like inside of the mission and some of the capabilities that we can use. And so the first thing I'm going to show is cargo aircraft taking off from the runway. There's a lot that got us here. We had to do the structural analysis, the design, the structural analysis, the aerodynamics of this, and we had to analyze and predict and understand the performance of this vehicle. So once we have all of that, we need to implement that all within the mission environment. Now we can say, if I had this cargo aircraft loaded with a tank or 2 tanks or passengers, will it be able to take off, successfully go? And what is the fuel efficiency? Should we fly it in a different direction? Should we fly it to a different area? And should we change in order to make it successful? So in the mission environment, in STK, you can design full route plans. You can do full route planning using the performance designed by computational fluid dynamics tools like Fluid. Additionally, with our route design, we can utilize drones, smaller aircraft, as well as multi-domain and GIS information like these points here. So there's some areas where it's showing radar coverage, I believe, and no-fly zones, and peaks where mountain regions are. And it's a very short video. I wish I had a longer version of this, but I just wanted to show how, in the future, this is currently how things are done. You can see the large, these are peaks and things that aircrafts have to avoid. But when we start looking at more drones and we start utilizing like the entire airspace, utilizing more and more of the airspace, we do have to get a little bit more granular, more accurate, and really simulate these things to a higher degree of fidelity. That might include full 3D modeling with buildings, and that's something that our mission tools STK can do. Additionally, we want to look at things like radar visibility. Radar visibility is another example of mission. Not only do you want to be able to fly from one place to another, but you want to be able to be detected or not detected. Sadly, I worked on the Malaysian Airlines, the flight that disappeared in the Pacific, down south. One of our customers and one of our users of STK was actually modeling the radars all along the coast of Malaysia and Indonesia in order to understand who could have potentially seen that aircraft. And since none detected that aircraft, what were the potential routes that this aircraft could have taken and who could have potentially detected it. And unfortunately, we weren't able to find the location of it due to the incomplete amount of data. After a certain amount of time, we did not have any more information, and just one ping occurred. So, in the future, going forward, it is important to model where these aircrafts are. Your mission is not just, the performance of the vehicle, but it's getting passengers from place A to B safely and securely. And, God forbid anything happens, be able to understand and recreate what happened. Not having radar visibility in certain areas, or not having a third, potentially like a ship's AIS solution, is kind of dangerous. So these are some of the analysis that you can run, radar analysis, very important. Additionally, as part of the digital mission engineering, we want to look at our communications. Communications is a big part of aviation. It's of course, and so one of the things I want to show you is the difference between a realistic and a simplified simulation. So in this case here, we have an aircraft. It has a communication antenna gain pattern. The antenna gain in red is a very high gain. So that's kind of its main beam width there. This is a very omnidirectional antenna, pointing out in all ways. This is a simplification of what the real antenna is like. So in this case here, we have a line. That line indicates a communication link. And so, yes, we have a valid communication link in this simplified analysis. But if we were to pull the full digital mission engineering, the full digital twin of the communication payload, we would actually notice that we've actually lost communication. That yellow line is hard to see, but it goes directly in this null region. So we were actually losing communication at the same time we expected communications. So our mission was not successful, or it was partially successful or partially failed, due to the disruption of communication that we've seen here. Additionally, we can perform, disrupt. We can use aircraft, and we can design and build disrupting technologies. This simulation is something that I did recently, actually, just a few days ago, and I wanted to include it here. This is a high altitude vehicle, and there's certain groups in US as well as Japan and probably other countries that are looking at high altitude aircraft to do communications. Instead of flying a satellite, they're going to fly a solar powered or long duration aircraft in circles above certain countries. And so what I did was I simulated it. I used electronic simulation as well as performance models that I got from a NASA mission, a NASA Pathfinder mission. And I was able to simulate what it would look like if we had high altitude aircraft, and what the overall communications mission was, that successful or not. And so in the simulation I ran, I was able to do communication effectiveness over the region. And so everywhere in blue is an effective communication. Everywhere in green and yellow is a low signal. And so what I found is this bird-shaped, this region here had very, very strong communications, which was very effective because there was a big mountainous range that had previously low to no communications due to the buildings of the terrain obstruction. But now, since this aircraft is flying quite high, it's able to communicate with those remote regions. And then the one thing I did notice is, running all this analysis, I actually had a very large gap. I had a very bad signal directly under the aircraft. That was just due to the antenna patterns themselves. So is my mission successful? I modeled everything. I modeled the performance. I modeled the communications. I was able to see, can I communicate with the remote regions in the mountains here? Yes, but partially my mission failed because I wasn't able to communicate with this certain region here. So I would have to say redesign. Maybe I redesigned my route change the configuration of my communication antennas, maybe rotate them, change different things in order to make my mission successful. And I might not have found out about that until I actually flew the test mission. The test mission, testing is very expensive. To actually fly an aircraft in test mode is very expensive. A lot of engineers, a lot of operators. But now I can run thousands and thousands of tests, millions of tests even, and I can understand how things are working without actually having to fly the system, the aircraft. And another example of flight testing, this was actually done by one of my friends and colleagues that I work with. He tried to do drone trials. So he bought a cheap drone and he did a mission plan. And he said, I want to follow this mission plan as close to the mission plan as possible. But what happened is he couldn't. His drone was too underpowered and he's not a good pilot. So he was off quite a bit. And so why I show this, and a drone that you can buy at a store with a credit card, is because you can simulate this with more advanced aircraft. It's very important to know exactly how far away or how much an aircraft is deviating from its expected route, and then understand why, and then try to figure out why it's actually deviating. Is it on purpose? Is something happening? Is the wind model not correct? Is there actually a larger wind expected in that region? Or was just something that the pilot saw and wanted to avoid? So there are many different reasons why you want to run pre-mission planning as well as post-mission planning, that as well. And then this could also be used for testing. So if you have test flights, you can model the test flights, you can figure out where they're supposed to be, and then the test flight shows you actually they're not performing as well as I expected, or the fuel usage is higher than I expected using this route. So the differences, we had a question, it was like, what's the differences between the simulation and the real world? Well, there's always going to be some differences, but the real key thing is understanding why there's differences. Why is there a difference between this and this? Is it because the communication antenna gain pattern is not correct? We actually maybe put the antenna on the wrong side of the aircraft, not the right fuel, not the right performance model. Something has changed. Like the differences between the simulation and the real world, those are the things you want to identify and understand. So let me go back. Let me go back to this, one of the original slides and talk about the legacy engineering process and how we would want to improve it. So how would we want to improve it? Well, we want to add more simulation. We want to add additional mission capabilities in order to optimize performance and optimize the mission. Not just can the vehicle fly, can it optimize the mission? So what we want to understand is external things like our ground station, our radar systems, as well as our communications. We need to understand those in order to have a successful mission. And I'll show you one main reason why we need to consider communications for safety analysis. So, or say RF, let me say RF for safety analysis. So another thing that we see in digital mission engineering is breaking down these barriers and integrating machine to machine, analysis to analysis, in order to not have engineers share files directly with the flash drive, but actually connect those tools together. So structurals, aerodynamics, thermals, electronics are all, simulations are all running together, machine to machine, and we're building up these models to be used later. We build up these models into these platform models, these system models. Attached are the payload models, attached are their capabilities. And then we build them in the reference mission. This reference mission could be multiple reference mission. You could have a mission, digital reference mission for every single route from every airport to every airport. And you could say which ones are successful, which ones need support, which ones have the expected fuel usage, which have too much fuel usage. How can we optimize those routes in order to get the best performance, the optimal performance? So the digital reference mission doesn't have to be just a single takeoff and landing. You could have thousands and thousands of digital reference missions, and that's the real value of these tools. And then overall, you can have them throughout the entire life cycle. These in the design phase, but you can also employ them in the testing and training phases, and also sustainment. You know, there was different groups. Part of my experience was I was in operations, and we actually had to change what our operations were due to some design failure. So instead of scrapping the mission, completing the mission, say the mission's done, we went back and we spent about a year to try to redesign the mission. We rebuilt all the tools that we had originally in order to redesign and redeploy and fix a mission that was done. If we were employing the concepts of digital mission engineering, a failure on board of this mission would not have been so devastating. You know, stock price plummeted. It was a huge issue, especially for the business side. So it's very important maintaining these processes and maintaining these models throughout the life cycle of a vehicle. And so I wanted to show you two examples of how we're actually using it. It's not just, you know, concepts and designs and ideas. You know, we are using these tools in real life, in everyday use. So the slides will be available. You know, if you want to screenshot and grab this URL, but the ANSYS blog has an amazing article about 5G and aircraft safety. This is one reason why I said, you know, it's important to not only have the performance of the vehicle, but also the performance of all the sensors and onboard payloads. So does the mission work? So this aircraft here is flying into an airport that has a 5G antenna. The 5G, Verizon, and AT&T in the United States purchased future C-band services at certain frequencies that are approaching the aircraft safety and radar system frequencies. There is a small guard band between them, but we still need to simulate the effectiveness and the interference that these systems have. So what ANSYS, my colleagues at ANSYS and AGI, and what they've done is that they actually modeled the transmitters from the 5G antenna and the receiver and the radar altimeter on the commercial aircraft. They flew this aircraft around where the 5G antenna was, and they said, what is the overall performance of that altimeter? And so I don't want to spoil everything, so please, it's a very short article. It has really good analysis, but there was a major effect due to the 5G antenna and the 5G frequencies on the altimeter itself. So there's ways that we need to figure out and mitigate it. ANSYS was, you know, actually provided a few ways, but yeah, it's very important that full mission modeling is done because of situations like this. And the last example before I wrap up is the GLADS program. And so GLADS is a U.S. Air Force program. It's actually software inside of the U.S. Air Force and the Air Mobility Command. And so U.S. Air Force came to AGI and they said, hey, we're having trouble with you know, collaboration between all mission partners across different warfighting domains for mission execution and flight following. This group was responsible for all cargo missions flying around the globe, and so they had, you know, tens to hundreds of aircrafts any given time carrying, you know, millions to billions of dollars worth of equipment in the air at any one moment. And so that was very scary for them, and they wanted to have an operational picture to reduce. And so the operational picture was done with AGI technology. So AGI technology like STK was integrated using web services, using web-based things, as well as a legacy and enterprise system data. It also used GOTS, government off-the-shelf technology, and implemented that into it. So STK as the mission tool was able to pull in different data feeds and run analysis from other tools and implement that analysis into its overall comp. STK was also able to run its own analysis within the tool for things like performance modeling, fuel usage, and line of sight like analysis. So right now it's currently in operations. It has saved what they told us, you know, what the tagline is save about $3.4 million per year in just man hours alone. So that's just a direct cost, a direct savings. But we've also reduced risk. We had there was a very large volcano eruption. I believe it was in the Atlantic Ocean. So it was Iceland. And there was a plume of ash and smoke that was spreading out towards Europe. And so during that time, there was cargo aircraft in the air that needed to be diverted. Using GLADS, using this tool that was just in the operational room on the screen right there, the commander was able to point out which aircrafts needed to be diverted and where could they be diverted, and was able to dynamically understand how much fuel was left in order to achieve that runway, and was able to get it. So it's very important as this is a digital mission engineering, and the mission includes multiple aircraft, not just a single aircraft following a single path, but an entire global mission. So just in summary, thank you for everything. So just in summary, I just want to kind of close with, digital mission engineering. Here are some tools that can be used from ANSYS. They can be replaced with other tools, but overall integration of the tools is very important. Integrating all your tools together in a digital mission engineering approach is very important going forward. Digital mission engineering is the key differentiator in increasing fidelity of these models, of current models. As designs mature and leaning on interconnected architectures, we support enterprise workflows. So increasing fidelity of the models is very important for analysis. Increasing efficiency. We don't want engineers to have to redesign and redeploy models that are already existing, already out there. We want machine-to-machine learning, so that the machine-to-machine interfaces, so that the systems can output the data, other tools. Oh. Sorry, I think I lost you. Am I still there? Okay. Sorry, just my computer broke. Okay, sorry about that. My computer died. And then finally, improving quality. Simulation capabilities supported by powerful data analytics, allow for the detection of defects early in the development, which improves failure detections and safety in operations. Also, reacting to failures in, say, the testing or operations phase allow you to, with digital mission engineering, easily start over and easily create new systems and update your systems. Additionally, digital mission engineering allows for disruptions. It allows you to employ advanced techniques, including AI or air mobility command or autonomous formation flying within the same framework as you're doing your current missions. So you can try out new things and new technologies inside of the digital mission engineering to see if those systems will work. And overall, achieve safety compliance. We allow for digital mission engineering, it allows for overall consistency of the simulation. It allows for traceability throughout the workflow. And these traceability, this analysis, this understanding, I believe is going to be required by a lot of safety organizations and safety standards around the world. How do you know that your aircraft is safe? How do you know it will fly as effectively as you expect? So that's digital mission engineering. I really hope you enjoyed the presentation. It was very hard for me to pull everything together and to sink it down into a few slides in just a short amount of time. I hope that was useful for you guys. And I'm always available for questions, and I know my full ANSYS team are also available as well.
Okay. Thank you, Mr. Alex, for your wonderful insights on design and simulation. So we have one question. How much of importance is given to testing versus simulation results during certification of an aircraft aero engine by regulatory bodies? That was the question, Mr. Alex.
Yeah. So we actually had some really good experience with that in the Joint Strike Fighter. Actually, let me scroll back to the one video. Not this one, but the one video actually shows the F-35. The F-35 is a fighter aircraft, and currently it's doing a lot of flight testing, and it's before it goes into operations. AGI was brought in as part of the test and evaluation program for Lockheed Martin because of their cost overruns. They were using traditional engineering processes and traditional testing processes in order, let me stop. In order to actually validate their simulation. So what's very important is that you're validating and understanding, is your aircraft going to fly? Is it going to perform in theater, in mission? And so what's really cool about SDK and our mission tools is that we developed a tool specifically for flight testing. It's called the T&E Toolkit, part of SDK Enterprise. And it allows you to pull in all of your data sets, all of your telemetry from a bunch of different data sources and overlay that inside of the mission so that you can understand if my aircraft was banking in a certain way, how much strain and stress was on that sensor. If I lose communications to the ground, why is that? Well, I was doing a barrel roll or some sort of very stringent test, or or I was flying low. There's many different ways to understand, will my aircraft be successful in mission, and T&E Toolkit allows you to do that. Before AGI got involved, a lot of the testing in T&E groups, part of the F-35 program, were actually just using Excel. They were scrolling Excel, and they were looking at if the data went bad, they would look at why, and they would look at the video, and they would just spend hours and hours trying to understand. When we started putting all of that Excel data directly into the mission environment, we were easily able to point out, oh yeah, that's the problem. that quick, oh yeah, there it is. Oh, that's it. Oh, obviously, those types of aha moments are very important when you have a very complex system and very complex analysis. So I hope that kind of answers the question.
Okay, thank you, Mr. Alex, for your answer. So with that, we are coming to the end of this presentations. We have covered extensively all the aspects of aircraft innovations, design and simulation with in-depth analysis and valuable inputs we have discussed. So with that, I now request Mr. D. Sheshadri, our Executive Director of SAE India, to deliver a vote of thanks. Yes, sir.
Good afternoon. Sorry for slightly being delayed from our program agenda. But I deem it a great privilege to propose a hearty vote of thanks at the end of this very interesting seminar. I must tell you, it is a well-rounded program. We had Boeing, we had GE, we had Honeywell, we had Infosys, we had Move, we had HCL, we had Collins, and most important, a group of people joined the first 1.5 hours from Ministry of Defense. They stayed together for 1.5 hours and listen to the presentations made. So that shows the importance of the subject and the relevance of people who contributed towards it and who made it a big success. I must thank ANSYS for co-hosting the program along with SA India and making this subject very interesting, interactive and participative. I must bring to your attention, Dr. Bala set the context for the program and outlined the roadmap in aircraft design and development for future. Thank you, Dr. Bala. And we also had Dr. Dipankar Chatterjee, who identified the next generation challenges and possible solutions. Thank you, Dr. Dipankar. Dr. Ravi Kumar of Infosys, he led the panel discussion, which was truly participative and interactive. And each panelist gave a very relevant value addition to the subject and in achieving sustainability in design and development. Technology chat, piloted by Mr. Amit Agarwal, focused on accelerating innovation in aircraft design. Thanks, Mr. Amit Agarwal. And finally, we had Mr. Alexander Ridgway, who gave a clinching presentation on maximizing mission performance using digital engineering, which is the latest context. Thank you, Mr. Alexander. And we thank all the participants who joined us in a reasonably good number, in spite of the fact that we started first in the morning on a working day. And we also thank ANSYS once again. And we pay our compliment to Mr. Hassan, who compared the entire proceedings throughout the day. Thank you. Thanks, all of you.
Are you passionate to become great aerospace engineer? Do you want to change tomorrow's aerospace industry? Are you passionate about emerging technologies in the aviation industry like uninhabited aircraft system, UAS? Come and participate in the Aerothon Design, Build and Fly contest being organized by SAE India Aerospace Forum. Aerothon aims to inculcate innovation mindset among the student community in emerging technologies like uninhabited aerial vehicles, UAV, incubate and nurture skills and capabilities of aero design in young minds and prepare them towards Atmanirbhar Bharat in critical aerospace technologies. Aerothon provides a platform for aero-passionate students to demonstrate aircraft design expertise and help develop the next generation of entrepreneurs. Aerothon will be conducted in 2 phases. Phase 1 invites innovative designs from the participant teams. The innovative designs will be evaluated by industry and academic experts. Top 20 teams will be shortlisted for Phase -2. During Phase 2, students build an unmanned aerial vehicle meeting specific mission requirements, culminating in a final fly-off event. Prizes awarded to 7 teams. Competition is open to all the students across India. Come participate in Aerothon and be part of Indian government mission to turn the country into a drone hub by 2030. Are you ready? you.